So I gave a presentation to the chapter in 2011 talking about the systems engineering methodology, or SEM, that LANL was in the process of rolling out. And so in a way, this is a progress report on that effort, which has now evolved into, from just being a SEM to the concept of mission assurance, because we had the dawning realization that while systems engineering is necessary, it is not a sufficient enabler of mission success. I'm going to start with a little bit of context. I know that many of you are familiar with LANL, so I'll cover these subjects fairly lightly, but if you have questions at the end, I'm happy to provide more detail. Most of the talk will be about the mission assurance framework itself and our implementation strategy and the artifacts that we have produced. We'll talk a little bit about lessons learned and current status, and I'll be the first to admit that we have a lot still to do, so I'll also review some of the next steps that we're contemplating. We are a multi-program laboratory where the projects are undertaken range from basic scientific research to proof of concept to demonstration of system prototypes in an operational environment. Some of these are best effort technology development where it's not clear that the goal is attainable, and so both the customer and the principal investigators commit to try to mature the technology to meet key performance parameters, but the acknowledgement is there at the outset that they may not succeed. Along the bottom, I have a number of pictures of actual LANL projects that illustrate the different scales of projects that comprise R&D engineering at LANL. On the left is a hydrostatic testing bench that was developed mainly out of commercial off-the-shelf components, but had a specialized purpose that required us to kind of build it in-house rather than just to buy a test bench. The next picture is of the aqueous processing line in our plutonium facility. The next is a laboratory-directed research and development project on wind turbines that was looking at improving the reliability of wind turbines, particularly the blades of wind turbines, which are subject to forces that had not previously been modeled. LDRD is basically an internal investment fund so that we can do technology or science demonstrations with the idea of perhaps then being able to find a sponsor for them. The next one is the ChemCam instrument that we currently have on the Mars rover. You may have read some things in the paper about this, the result of finding boron on Mars. So it was this instrument that found that. That was a project that was, JPL was the lead systems integrator, and so we had a systems engineering lead for our instrument, but it had to be integrated with all of the other instruments that were going on the rover. And then the final picture is the W-76 nuclear weapon, which is carried by the U.S. Navy's Trident missile submarines. I know some of you have been to Los Alamos, but one of the things that makes integration of R&D difficult here is the size and geography of our campus. So we cover over 40 square miles. We have quite a number of different technical areas. What you see on the map, that the numbers that you can't read, each of those numbers and the colors are indicating a different technical area. We have lots of different types of facilities. The picture on the right is a mile-long linear accelerator, but we also have explosive sites. We have a high magnetic field lab. We have numerous light lab kind of facilities. Yeah. And then the other thing that I want to call your attention to in the picture on the right is that the lab is built on a series of mesas. And so if you see on the bottom right-hand side of that picture, there's a road. Those of you, and it's quite a bit further down from where the facility is. Those of you who have been to Los Alamos, that's the truck route. And so I travel to this facility fairly frequently, and it's about a mile and a half from my office, but it takes me 12 minutes or so to get there because of the terrain. LANL employs nearly 10,000 staff members, about 30% of whom are scientists and R&D engineers, and another 30% are technical support staff, by which I mean various flavors of technicians and technologists. The R&D engineering staff, by which I mean people whose job title is R&D engineer, postdocs and GRAs whose terminal degrees are in engineering. So that's what's in the bucket that is R&D engineering staff. Is about 43% of the overall professional R&D workforce, and that number's about 1,000 people. On the left-hand side, you see an org chart of the directorates in the laboratory. Directorate is basically a VP-level organizational unit. We have 2 dedicated R&D engineering directorates, one for weapons and one for the non-weapons. I'm in the non-weapons rather. Quinn Fatherly, who just introduced himself, is in the weapons side. So we are very distributed. As you can see on the right-hand side, this is the distribution of R&D engineers by directorate. And what you see is that although the weapons directorate really, is the largest, there are lots of other competitors, and the directorate that I'm in, the Engineering Sciences Directorate, which was set up to be the non-weapons R&D engineering directorate, is smaller than some of the other directorates that have pockets of engineering. There's also something not shown on this graph, which is that we have a non-R&D facilities engineering division, which is the organizational unit one lower than the directorate. But those workers are not reflected in any of these numbers that I'm showing you here. This chart shows the terminal degree disciplines of the R&D engineers. They come from diverse technical backgrounds, but there are very few that have a terminal degree in systems engineering. And even if you assume that IEs came from programs that included systems engineers in the curriculum, as I did, that number is only about 21, which is 3% of the population. So most of the people on the non-weapons side do not identify as systems engineers, even if they are, in fact, performing some systems engineering tasks. Discipline engineers in the weapons side are more likely to do that. On the non-weapons side, my estimate is that it would be about 30%, 30 people would be all that would identify that way. And that factoid becomes important when we talk about one of the implementing tools, which is the mission assurance support tool that I'll talk about later. The bottom line is that many of these people have little understanding or appreciation of the core concepts of systems engineering, project management, or engineering quality and rigor. And so that is one of the complicating factors for how we disseminate this mission assurance framework. Another kind of quirky thing that maybe the Sandians will know about, but probably no one else would, is that on the facility side of the house, there are people who are called cognizant systems engineers, which is a term of art in the DOE complex, but isn't what we think of as a systems engineer when we're talking about what a systems engineer is. It's an engineer who is responsible for a safety system like HVAC in a nuclear high hazard facility. So in some cases, when we say the word systems engineer here, that's where people's minds go, and they say, that's not what I do. And so that's, you know, just another layer of complexity. But enough of my complaining. I want to move on to, you know, what is this mission assurance framework. But before I do that, I want to give a shout out to Ann Hodges, who provided a previous version of the figure that you see on the right here that we adapted for our purposes. So I thank her for that. Early on in our development process, Sandia was out ahead of us, and Ann was kind enough to share what they were thinking about and doing in their area. So in any event, the definition of the mission assurance is the graded application of systems engineering, project management, and engineering quality and rigor. And the point of this is ensuring that we deliver quality products and services to our customers on schedule, within budget, to achieve mission success. So our SEM originally incorporated both systems engineering and quality assurance, and I'll talk a little bit about that in a minute. And they focus on the health of the product. And so what the project management piece adds to this table is a focus on the health of the project. I'm going to talk about an infamous now project here at the laboratory that is the prototypical example of why we needed a mission assurance framework. The project was called Angel Fire, and what it was a prototype demonstration of a persistent surveillance system that allows soldiers in the field to maintain situational awareness of conditions in the battlefield. The project was wildly successful. The customer brought this project to the laboratory just shortly after Thanksgiving one year, and it was executed in a very short time frame, basically over the Christmas holiday. So it was like the first week in January where this thing was delivered in the field. The field deployed units loved it. And so, you know, you would think that this was the world's greatest success story, but it turned out not to be. The problem was that the military wanted more units pronto. And normally this, you know, occurs in a tech transfer kind of a way where, you know, we turn over our or license our design to a company for commercialization, and then, you know, manufacture and commercialization to a DoD contractor. However, in this case, there wasn't anything to turn over. We had to spend lots of time and money to reverse engineer the system because there were no drawings, no system description document, no manuals, no fill in the blank. And the first article was in the field, and we weren't getting it back. So that was, you know, an extreme case. I could give others, but, you know, this one, people really kind of grab on to this as, oh yeah, now we see. Said in a more boring way, the drivers for adopting the risk-based enterprise SEM and eventually the whole mission assurance framework was based on a series of beliefs about what that would do for us, and that those beliefs are consistent with the values that INCOSE espouses for why one would want or need to use systems engineering. Notice how the drivers also relate to improving project management, which made the evolution to the mission assurance framework a logical thing. Our implementation strategy was to first develop policies, procedures, and implementation guides, then tools to support implementation, and finally training. And training came along much the latest thing in the process, in the procedure, you know, in the process, for reasons that I'll get into when I start talking about the training. implementation strategy was governed by feedback from internal stakeholders, as well as a lesson learned that was provided by Miller, who says tools can only help if there is a decent process in place. So the first few years of this really focused almost solely on the policies, procedures, and guides. The talk will focus mainly on the conduct of engineering for R&D, which is actually a program document, and the determining needed engineering rigor for R&D, which is a procedure that implements one piece of the conduct of engineering for R&D program. The 7 implementation guides are listed there. I will note that for good or for ill, I am the author of all of the documents for the bullets except for the project management for programmatic and R&D work, which I was a contributor to, but I was not the lead author for. So conduct of engineering for R&D really is the LANL SEM. It's a governance document that is helping us to ensure consistency in a very distributed enterprise, which is a challenging thing. So what we say about the conduct of engineering for R&D program is that it's the glue that connects the R&D engineering community and ensures consistency across the multiple organizational entities that have R&D engineering responsibilities. It's the how we do R&D engineering at LANL, and it has been described as the equivalent of the scientific method for engineering. It was important to us that our policies be standard-based, and so it was based on the ISO 15288, as well as the INCOSE Systems Engineering Handbook version 3.2.2, which was the version that was in place at the time that we were developing this. The conduct of engineering for R&D policies and procedures address 2 of the 3 elements of the mission assurance framework, the SE methodology and quality, and they use a risk-based graded approach to determine how much systems engineering and engineering rigor must be applied. As you can see in this diagram, the intent is to apply steps iteratively, but to allow recursive nature as things need to be revisited as a project progresses. And organizations don't have to use this as one size fits all. They have the option of tailoring to accommodate concurrent engineering, agile, or other engineering approaches. We have one organization that uses a lot of value engineering, and so they've taken this and turned it into an internal document that incorporates the value engineering concepts. Now, those of you who are systems engineers may be surprised to see a waterfall model rather than the typical V, but that was deliberate. And basically we're using all of the same elements that are in the V model, but using simpler concepts to express them. This was driven by a requirement to use language that was familiar to the R&D engineering community rather than SE jargon. And those of you who have known me a while know that I talk about stealth SE, getting those concepts in there without necessarily using all of the terminology. So test and evaluation are methods for V&V of the system, but that test and evaluation is commonly understood by our R&D engineers. We used best practices, again, from Miller, who advises looking at problem areas when deciding what parts of the process to tackle first. And so we decided to work on requirements and configuration management as our prime areas. we did, as you saw from the list of implementation guides, we eventually did cover the full systems engineering life cycle, but the early emphasis was on requirements and configuration management. The lab, as you might imagine, has a complete quality assurance program, and the conduct of engineering for R&D piece implements the design chapter of that program for the research side of the house only. And again, we are standards-based, and in this case, we're following an ANSI standard called Quality Guidelines for Research. That was a bit of a bloody battle when we undertook it, because the mindset is that basically all of the quality assurance needs to be up to the caliber that one would expect for items going into a nuclear facility. And we pushed back on that and said, no, it has to be sufficient to ensure research integrity, and it also has to be sure, that the quality is sufficient so that there's an assurance that a product that we're sending out the door has the ES and H risks are mitigated, I guess is the best way to say it. So the procedure, which is, as I said, a companion document to the Conduct of Engineering for R&D program description, uses a risk-based graded approach to figure that out. And so what it does is determine the required degree of rigor in reviews, approvals, and documentation, where activities that are designated high risk, get the most controls, but nothing gets away scot-free. So there's a baseline that applies to every project, and I'll show that here on this next slide. So the way that this works, excuse me, I have to cough. Okay. The way that this works is that when a project is initiated, the responsible line manager makes a determination about the level of rigor that's required based on a qualitative estimate of the probability and consequence of failure of the engineered product at any stage of the system's life cycle. So it could be a failure during development, it could be a failure once it's fielded. We provide in that document benchmark anchor exemplars for safety, security, health, environmental, and mission risks and consequences. And so the manager has to look at the particulars of the system under development and try to make a gauge of where that system falls in the high, moderate, or low risk along the way. And you see there, then that determination tells you what level of formality is needed. And the thing to note is that the documentation requirements are cumulative as the risk level increases. So all projects have to have a risk level determination review to determine what are the applicable standards, and a written statement of need or problem definition. And then additional requirements for documentation come into play for moderate and high hazard. And the other thing to note about this was that for low-risk products, R&D products, the documentation may be very informal. We allow people to use notes or sketches in a lab notebook, for instance, for documentation, where that's appropriate. And then we have to have conversations about, well, what does configuration management mean in that kind of a context? So that for that example, what we tell people is, well, when you put it in your lab notebook, date it, and if it changes, redline it, date the red lines, and kind of keep a running tally of changes that were made and when and why. and that kind of started to resonate with people a little bit because they were kind of used to updating their experimental protocols in that kind of a fashion. And so after a lot of resistance initially, we kind of got that into people's heads. Sorry, I've got a bad cold. I'm okay if I don't talk too much, but the only other part, point that I want to make on this slide is that the manager who participates in the project reviews is the risk acceptance authority for the institution. Sorry. And so that was another line of contention between senior managers and lower level managers. Because the lower level managers basically said, I'm the one who controls the the day-to-day work and the risks associated with that work in my organization. And some of the more senior managers, particularly with respect to this higher risk level, say, well, wait a minute, shouldn't a senior person be accepting high risk? The ADs, associate directors, did eventually agree to let that reside down a level, but there was a lot of conversation about accountability. So, okay, we will delegate that down to the next level. However, woe unto you if you don't keep me informed before you accept something high risk, and and engage me in the conversation. So that was another kind of sticking point that we had. As implementation progressed, we certainly started to understand why systems engineering and engineering quality and rigor by themselves weren't going to cut it. And kind of the best example of that is we do a lot of satellite-based sensor systems, but they're going to be worthless if they are delivered too late to meet the customer's scheduled launch date, right? So you need the project management to ensure that you actually deliver the quality products and services that you are contracted for to ensure that the mission is successful. So you need that project management rigor to make sure that the product works out okay. The only leg of the stool that wasn't developed as we started coming to this realization was the project management piece. And so, as I said, we did develop the project management for programmatic and R&D work. Up until that point, we had very rigorous project management on the facility side of the house and very lax, no, actually lax isn't the right word. We were trying to apply a square peg to a round hole on the R&D side. So we would have, project controls people who were very familiar with project controls for construction, but didn't understand this concept that I had said before of, in many cases, it's best effort. And so how do you translate earned value management into an R&D environment? So we got some help from the project management people, but people who had been working at the laboratory and in R&D environments for a long time. Those of you who are PMPs or PMI members, this will look very familiar to you. Basically, the LANL document is a simplified version of the project management body of knowledge, which is also an ANSI standard. So now we have all three of our legs of our stool being standards-based. I'm going to move on to tools now. That was more about policy and procedure than probably we really needed, but it kind of it shows the evolution of how we got to where we are today. Some of you know I spent 4 months in residence as a visiting professor at the Naval Postgraduate School, and then worked with their students for another 3 months to complete something called the Mission Assurance Support Tool. No accident, I don't think, that it's called MAST, with the 6 Navy lieutenants having developed it. And then we also have, and let me just tell you what MAST is, and I'll give you more details about it in a minute. It's basically a very simple query-based tool intended for people who don't know a whole lot about systems engineering to guide them through the system development life cycle. The requirements generation tool is intended for more sophisticated users who need support for requirements elicitation and rigorous documentation of requirements. At present, at least, the requirements generation tool does not support the full SE life cycle. It focuses on the requirements. I'll show you these two things in the next few slides. If there's time at the end, I can show you a live version of MAST if people are interested in seeing it. Alternatively, MAST will be available on the chapter website. It has been approved for external release, so anybody who is interested in trying it out can just have at it. You have permission to use it as you wish. So development of the Mission Assurance Support Tool was a collaborative project between LANL and the Naval Postgraduate School, facilitated by Cliff Whitcomb, who was the Systems Engineering Department chair at the time. He has since stepped down from that post, but he's still on faculty there. And it was in the context of the students' design thinking classes. So the goal that you see there is the design challenge that was given to the students at the outset of that course. And so they used the design thinking process in developing the tool. The first piece of which is empathy, getting into the heads of the users. And so they conducted phone interviews with R&D engineers and managers, and that resulted in a refinement of the problem definition to be, how might we create a tool that is applicable to any project and that will aid in the design process and ensure all important factors are being considered. They used that and several other how might we kinds of statements to derive requirements, some of which are shown on the slide, and there were quite a few more. The other requirements were that it be comprehensive, incorporate the full system life cycle, use terminology consistent with LANL policies and procedures, serve as an aid in the engineering design process, ensure that all quality affecting factors are considered, and facilitate documentation and configuration management while minimizing bureaucratic activities not contributing to the quality of the engineered product or customer satisfaction with the product. I mean, the students, in fact, were adamant that it not add work to the engineer's tasks, that it just facilitate the work. The goal here is to document a project so that if it has to be duplicated or pursued further at a later date, like the angel fire problem, we want more of these, complete documentation is available or at least is cross-referenced in one file. The tool initially focused just on the systems engineering topics that you see on the right-hand side of the screen. It has since been incorporated, modified rather, to incorporate project management queries, again, at a fairly high level: who's working on the project, when does it have to be done, where's the funding coming from, and questions like that. The MPS students also developed a user's manual and an example, and unfortunately I have not kept pace with that on the PM side of the tool, but it's on my to-do list. It may eventually get to done. The requirements generation tool is much more sophisticated than MASC, and for use where more formality is needed in applying the SE process. It does not include any project planning. It does not include any risk level determination, and it probably won't anytime soon. The one thing that we do hope is that eventually it can be modified so that we can export from the RGT into commercial products like doors. Okay, now turning to training, we have implemented one piece of training and have more in the pipeline. There was initial internal resistance to the idea that discipline R&D engineers needed training on the fundamentals of the conduct of engineering for R&D program, but what we found was that there was a lack of penetration of the mission assurance framework to the working level, that the policies, procedures, and tools were not getting used. There was an audit track waiting to happen, if nothing, not anything worse than that. And that was partially because of how the Conduct of Engineering for R&D engineering program came into existence. So we have something here called the Engineering Steering Council, which is intended to herd all the cats that have R&D engineering work going on in their organizations and get them to some level of agreement about what the consistency of policies, of practices ought to be. And so they were on board, but they tended to be higher level managers who didn't really do a very good job of promulgating that through their organizations. So we, in my director, it was no different, even though I'm sitting here and could have done that. We anticipated doing something called a management self-assessment, where we would go and look and see how the implementation was going. And then we realized that there wasn't a whole lot to look at. You didn't have to leave your chair to know, that there wasn't penetration as you kind of were talking to people or seeing the work products that were coming out. And so that lack of penetration was an enabler for us to be able to roll out to use training as a mechanism to get the word out and to develop a common vocabulary across the R&D and engineering enterprise. So, this is kind of the first step in developing a mission assurance culture. I'm going to show you some of the training materials here in just a minute, but I also want to talk a little bit about how this is being deployed, because this idea that, well, people who have been here for a long time, have we don't need to tell engineers how to do their job, I guess was the primary complaint there. And so there was a lot of pushback from the incumbent R&D engineers. And so this Engineering Steering Council came upon what has turned out to be a pretty good strategy for implementing, and that is that we have rolled this out to all of our early career R&D engineers on the non-weapon side only at this point. And so the early career was defined as 5 years or less of employment here. And what we're seeing happen is that gets them early enough that they're not really indoctrinated in different work processes, but they also go back to their home organizations after the training is done and say, hey, why are we doing things this way rather than following this conduct of engineering for R&D program? So the ones who really grok to the training have become advocates for us in a lot of cases, which has been a very interesting dynamic to watch. We have gotten through all of the early career hires as of this past fall, and so we did a number of sessions to pick them all up, and now we're anticipating that what we'll do is just do this once a year and pick up all the new hires in that 1 year. Okay, so this chart's essentially the syllabus for the R&D engineering primer training. In putting the primer together, we wanted to present systems engineering, project management, and QA the way that the work actually gets done. When I first started this, I was going down a path of, let's have a module on systems engineering and a module on project management. It's like, no, that's not how work gets done. So we came up with this chart. Actually, this was something that I was working on while I was at the postgrad school. So I had all these flip charts hanging on the walls of my office, developing this graphic. The focus is on the what and the how, the activities and artifacts performed during the concurrent project management and systems engineering life cycles. The blue are the systems engineering activities and artifacts. The green are the project management, and the red are the quality. The bold are the ones that are most thoroughly covered in the training. Some of the others, we mention what they are, but there's not a lot of attention paid to them. And there's one tricky one that if you have good eyes, you'll see under initiating, stakeholder list is both green and blue, because it's one of the things that is often shared between the systems engineer and the project manager if there are two different individuals in those roles. We used a home improvement example that was published by our INCOSE Netherlands colleagues because we agree with them that using real local engineering projects as examples often results in people getting so wrapped up in the technical details that they miss the systems engineering concepts that we're trying to convey. We've seen that both in materials that we have developed and also when we've brought in outside training organizations we had a university that their continuing education program, and the school will remain nameless, but all of their examples were Air Force related or aircraft related. And people here, it was like they're trying to understand the technical details, but they didn't necessarily understand them. That's not their world. And and with a multidisciplinary lab like ours, there's almost nothing that you could pick that you wouldn't have that problem with. So the only purpose of this slide is to explain what the scenario is. It's basically a couple who has been rearranging their furniture time after time, trying to get better living space for themselves and their existing child and their child that's on the way. And so the way that we do this is we put out whatever the part of the scenario is with a short discussion of the concepts to be explored. And so in this case, it was the statement of need, and make the point of what a statement of need is, where does it come from, and that in this case, it may come from the customer, but the job of the systems engineer is to translate the customer need into a definition of the problem that not only represents the views of different stakeholders, but also keeps the potential solution space open. And we use quick drills, 2 to 5 minutes, just depending on what it is, working in groups of 4 or 5 to produce an artifact, in this case, a statement of need. And so here, almost invariably, the statement of need that people come up with, and our Netherlands colleagues came up with as well, is that the couple needs a bigger house. And we talk about things like a better alternative being something that leaves the solution space open. So they need living spaces that will accommodate their lifestyle preferences. And then we follow that with a debrief and a large group discussion. This is another piece, again, moving through more of the scenario. This one actually does a better job of showing what happens in the class. So we've moved the slides forward, and we're beginning to talk about requirements and constraints. This is a duplicate slide. Sorry about that. And go ahead and talk about what are functional and performance requirements, what are constraints, provide some definitions and that sort of thing. Talk about what are the key characteristics of good requirements, and then some of the things that you really need to be paying attention to. This idea of it's a what. The requirement defines a what, not a how. You need to maintain traceability, that you need to be developing your measure of performance for your requirements as you're developing your requirements. And then this freeze requirements early, but change them when necessary, and talk a little bit about why user requirements change, and that it's almost inevitable, but it needs to be done through a managed process. More, there we go. Improvement project, and to give people practice in doing that. The way that I do this is I have in the slide deck, the slide that you're looking at is in the slide deck, so that in the event that the trainees don't bring out all the points that I'm going to want to bring out, I have a way to do that. So, for instance, on this one, almost no one, even though we talk to them about it, develops measures of performance that can be verified in different ways as the project progresses. So this is an example of that. Okay. On to lessons learned and current status. As I said earlier, the internal stakeholders gave a lot of feedback that confirmed the need for the stealth systems engineering approach. Basically, as we were developing the primer, as we were piloting the primer, a lot of content that I would like to see in it has fallen by the wayside because it was too jargony in the opinion of the people who participated in the pilot. We have not done a rigorous implementation assessment, but informal CMMI self-assessment found us somewhere between level 0 and level 1. We would definitely take the stealth SE path again, and we'll continue to use the waterfall model and less strict systems engineering vocabulary until we can assess ourselves at least the CMMI level 2 managed. We still have a long way to go. As far as the implementing documents, as I said in the beginning, we built this on handbook version 3.2.2, and we need to review for consistency with version 4 and update as needed. And version 4 has done a lot of good stuff, particularly in the stakeholder analysis phases, that I think it would be beneficial to us to go ahead and weave into ours. Some of the feedback that we get from the students in the primer is about requirements, and well, you get them from the customer, and it's like, really? Yeah, yes, and if you don't understand the problem that the customer is trying to solve, you're going to have the wrong requirement set. So that's an area that I think we could benefit from more attention to. The risk grading approach, as I said, was qualitative based on probability and consequence. And we've gotten feedback that that's too complex, especially because there's no clear guidance on how to set the anchors for the qualitative evaluation of probability and consequence, just examples to be customized for each project. And so we're reassessing that. At the 2015 International Symposium, a group from PNNL talked about a TRL-based approach for risk grading, and we're looking at that as a potentially simpler alternative. And then the other thing is that risk grading as it is now really only addresses the technical system risks. And so we're using that to guide how much engineering quality to apply. But we do not at present, and we need to, also assess project risks to use as a guide to how much project management rigor is needed. On the tools front, we had intended to incorporate a risk grading component into MAS, but that's on hold since we don't know where we're going with risk grading. There's no point in doing that right now. And then, as I said, the requirements generation tool is expected to evolve to fully enable requirements traceability by allowing export into commercial requirements tools. We have a pilot application of the RGT requirements generation tool for evaluation purposes underway. Training was always planned as a multi-tier package, with the R&D engineering primer having a basic or foundational focus, wanting to get common vocabulary out, and being geared to how to implement key elements of the framework. We also have a more comprehensive mission assurance framework course that has been developed but has not yet been delivered, that explains why we do the things the way we do, more in depth on the key concepts, and intended for more senior technical leaders and for principal investigators. But I have no idea if and when that will ever roll out at this point. And then the other piece, which is being rolled out, is an executive briefing aimed at senior line and program managers that stresses the importance and benefits of implementing the mission assurance framework, why LANL should care, why we should invest in the framework, that, you know, I think until we have the buy-in at that level, we won't make progress in getting this really fully implemented. It was interesting, about a year or so ago, I and a few other people briefed the lab director, and he said all kinds of nice words. One of our mission assurance framework slides that we use with our trainees has a quote from him about, we really need this to ensure mission success. But there has been no push from the top to really be sure that it actually is implemented. And then finally, on metrics, as I said, this informal assessment on CMMI has been the only thing that we've done. What we need to do is to develop objective progress measures to include implementation penetration, indicators of improved organizational effectiveness, and start having periodic management assessments of implementation.